Hello everyone, my name is Vijay Aditya and this presentation is a part of my mentorship with the Open Mainframe project under the guidance of my mentor Suresh Tadisetty and with the support from the Linux Foundation. I have worked on modernizing mainframes using Agentic AI. Mainframes continue to run some of the most critical workloads in the world, but modernizing them is not easy. Dependencies between COBOL programs, JCL job flows, DB2 databases are opaque, making it hard to understand what depends on what. And also, organizations rely on tribal knowledge, that is, expertise locked inside a few individuals, which processes a major risk as people retire. There are also frequent cost spikes, often caused by insufficient job scheduling or resource usage. And most importantly, modernization is slow and risky because enterprises fear breaking what already works. So now let's imagine if what if the mainframe could modernize itself? What if it could answer its own questions, tracing dependencies and risks automatically? What if it could optimize costs, reschedule jobs, and reduce MSU consumption? What if modernization became continuous with refactoring and governance built in? And what if all this was done with trust and safety, ensuring that no wrong change ever reaches production? This is the vision behind our architecture. So, our architecture consists of 4 layers. Each layer performs different functions. Each layer plays a distinct role, and together they create a modernization pipeline that is trustworthy, safe, and resilient. The layer 1 is the interface and session layer. It provides multiple access channels, a web console, a command line interface, chat interfaces, and APIs so users can interact with the system in the way they are most comfortable with. It is secure by design with single sign on, multi factor authentication, and role based access controls built in. Finally, it has context awareness. It remembers session histories and time windows, so follow up queries feels natural and not repetitive. The layer 2 is the knowledge intelligence engine, essentially the memory of the system. At the center is a knowledge graph that maps all the relationships between programs, jobs, databases, DB2 tables, CICS transactions, and ADRs. ADRs are architecture decision records that are important. These are lightweighted documents that capture key architecture decisions. By embedding ADRs into the knowledge graphs, the system just doesn't know what exists, but also why the choices were made. This ensures that the future modernization aligns with past governance and decisions. Also, this layer uses an hybrid RAG architecture that allows both lexical and semantic search across code, documentation, runbooks, and incident history. To make this memory trustworthy, we use a dual source reconciliation combining static phrases with runtime traces, and we store these relationships in a conference code graph. The layer 3 is the MCP orchestrator, which acts as the traffic director of the architecture. The MCP takes the roadmap from the context builder and converts it into an execution DAG, as shown in the image, a JSON graph of tasks with explicit dependencies. Each task is then routed through one of the three paths: a policy router that handles 80% of the tasks, which are well defined tasks, the LLM planner, which handles around 15% of complex or novel tasks where decomposition is required, and about 5% of the cases that trigger human evaluation where a risky task becomes an approval node in the DAG. Before any execution, the plan validator ensures schema correctness RBAC, and policy compliance, and both pre and post execution checks. Finally, every task execution emits telemetry and audit logs which feed back into the knowledge intelligence layer, continuously strengthening the system's memory. Finally, the layer 4 is where the actual execution happens through a set of specialized agents. A cost intelligence agent monitors MSU usage, suggests jobs reschedules, and tunes resources to control costs. The performance and impact agents simulate workload changes, predicts bottlenecks, and validates optimizations before they reach production. The modernization agent identifies refactoring opportunities in legacy code, generates ADR drafts, and ties every modernization step back into governance. And the operational control agent safely executes jobs, enforces schedules, and handles operational commands with right safeguards. Together, these agents execute tasks passed down from the DAG in layer 3, and they report telemetry back into the system for validation, auditing, and continuous learning. This loop closes the this closes the loop, making modernization not only automated but also accountable and safe. This slide explains how the architecture guarantees operational reliability, because enterprises won't trust automation unless the design is safe. First, we have pre-checks. Every DAC plan is validated for schema correctness, RBAC and policy compliance, and checked against change windows before execution. Also, for risky or high impact tasks, we use human in the loop. These become explicit approval nodes in the DAG, so a person must sign off before it executes. Third, we ensure rollback and recovery. We run shadow and canary executions, and if any SLA is breached, the system automatically rolls back to a safety state. Finally, everything is logged in an audit trail. Every action has provenance and evidence, making the entire process fully traceable. In conclusion, mainframe modernization is not a one time migration but a continuous practice. It requires balancing automation with governance and innovation with safety. This layered architecture of the MCP knowledge graphs and specialized agents enables modernization that is trustworthy, auditable, and resilient.
This mentorship gave me the opportunity to gain a much deeper understanding of mainframes from COBOL and JCL to SMF data, DB2, and overall operational workflows. After the mid evaluations, I realized some key learnings. First, the importance of governance first design. Modernization is not just about converting code but ensuring trust. Second, the value of ADRs in capturing decisions so that future steps are explainable. I also learned why human in loop validation is essential for risky tasks. And finally, the parser complexity. Extracting metadata from COBOL, JCL, and DB2 taught me why combining static parsing with runtime traces is so important. Through this process, I developed skills in layered architecture thinking, adopting a governance first mindset, and learning how to balance automation with safety. And my biggest takeaway in this mentorship is that modernization is not just a technical migration. It is about building trust, governance, and resilience into critical enterprise systems. Finally, I would like to express my deepest gratitude to my mentor Suresh Tadisetty for his valuable guidance and constant support. I am also grateful to Tom Sanda, manager at the Linux Foundation, for ensuring a smooth and enriching mentorship journey. And finally, I thank the Open Mainframe project and the Linux Foundation for providing this valuable opportunity to explore mainframe modernization and contribute to the future of enterprise systems.